The complete explanation of switching voltage regulators and its application. Switching voltage regulators are electronic devices used to control the voltage level in electronic circuits efficiently. They are commonly used in various applications, including power supplies for electronic devices, battery charging systems, and voltage regulation in automotive systems. Here's how they generally work and some key points about them. The basic principle behind switching voltage regulators involves rapidly switching a semiconductor device, typically a transistor, on and off to control the flow of voltage. Here's a more detailed explanation of this principle. Controlled switching. Switching regulators utilize a controlled switch, usually a transistor, that alternates between fully conducting, on, and fully non-conducting, off, states. This switching action is controlled by a feedback mechanism that continuously adjusts the duty cycle, the ratio of on-time to total period, of the switch based on the desired output voltage. Inductor-capacitor energy storage. In switching regulators, energy is stored and transferred between an inductor and a capacitor. When the switch is turned on state, current flows through the inductor, storing energy in its magnetic field. During this time, the output capacitor supplies power to the load, maintaining a stable output voltage. Energy transfer. When the switch is turned off (OFF) state, the inductor releases the stored energy, causing the magnetic field to collapse. This results in a voltage across the inductor with reversed polarity. The diode, often called a freewheeling diode, connected across the inductor allows this energy to continue flowing to the load, maintaining the output voltage. Regulation. By adjusting the duty cycle of the switch, the regulator can regulate the output voltage. If the output voltage tends to rise above the desired level, the duty cycle is decreased, reducing the amount of energy transferred to the output. Conversely, if the output voltage drops below the desired level, the duty cycle is increased, providing more energy to the output. Efficiency. Switching regulators can achieve high efficiency because the switch operates in either fully conducting or fully non-conducting states, minimizing power dissipation. Unlike linear regulators, which dissipate excess energy as heat, switching regulators transfer energy to the load more efficiently. Types of switching regulators. There are several types of switching regulators, including buck, step-down, regulators, convert a higher input voltage to a lower output voltage. Boost, step-up, regulators, convert a lower input voltage to a higher output voltage. Buck-boost regulators can step up or step down the input voltage to maintain a constant output voltage. Flyback and forward regulators, used in isolated power supplies and other specialized applications. Overall, the basic principle of switching voltage regulators involves controlled switching of a semiconductor device to efficiently regulate voltage by transferring energy between an inductor and a capacitor. This principle enables the design of compact, efficient power supply solutions for a wide range of electronic devices and applications. Efficiency is a crucial aspect of switching voltage regulators and is one of their primary advantages over linear regulators. Here's a closer look at efficiency in switching voltage regulators. Minimized power dissipation. Switching regulators achieve high efficiency by minimizing power dissipation. Unlike linear regulators, which regulate voltage by dissipating excess energy as heat, switching regulators transfer energy to the load more efficiently. Switching action. The key to efficiency in switching regulators lies in their switching action. The semiconductor switch, usually a transistor, in the regulator rapidly switches between fully conducting and fully non-conducting states. This rapid switching allows the regulator to control the flow of energy with minimal loss. Reduce losses. When the switch is in the on state, it conducts current with minimal resistance, allowing efficient transfer of energy from the input to the output. Conversely, when the switch is in the OFF state, the energy stored in the inductor is transferred to the load via a diode. This process minimizes losses associated with energy transfer. High efficiency range. Switching regulators typically operate with high efficiency over a wide range of input and output voltage levels. This versatility makes them suitable for various applications where input voltage may vary, such as battery-powered devices or systems powered by fluctuating power sources like solar panels or wind turbines. Losses and efficiency factors. Switching losses occur during the transition of the switch from on to OFF and vice versa. These losses depend on factors like the switching frequency and characteristics of the switch. Conduction losses, associated with the resistance of the switch when it's in the on state and the resistance of other components in the regulator circuit. Inductor and capacitor losses. Although minimal, losses can occur in the inductor and capacitor due to their non-ideal characteristics, such as resistance and equivalent series resistance, ESR. Control circuitry losses. The control circuitry of the regulator can also contribute to overall losses, although modern designs aim to minimize these losses. Efficiency considerations. Designers must carefully consider various factors to optimize the efficiency of switching regulators, including choosing appropriate components with low resistance and high efficiency ratings, selecting an optimal switching frequency to balance switching losses and other efficiency factors, implementing efficient control algorithms and feedback mechanisms to regulate output voltage accurately. Overall, switching voltage regulators offer high efficiency and are widely used in applications where energy efficiency is critical, such as portable electronics, renewable energy systems, and automotive electronics. Their ability to minimize power dissipation makes them essential components in modern power supply designs. Switching voltage regulators consist of several key components that work together to efficiently regulate voltage. Here are the main components typically found in a switching voltage regulator. Switching element. Transistor. The heart of the switching regulator is the semiconductor switch, usually a transistor, such as a MOSFET or a BJT. The transistor controls the flow of current between the input and output circuits by switching on and off rapidly. Inductor. Energy storage element. The inductor stores energy in its magnetic field when the switch is on and releases it when the switch is off. It smooths out the output voltage and current, helping to maintain a stable output. The value of the inductor affects the ripple voltage and the response time of the regulator. Diode. Freewheeling diode. In many switching regulators, a diode is connected in parallel with the inductor to provide a path for the inductor's current when the switch is off. This diode, often referred to as the freewheeling diode or flyback diode, prevents voltage spikes and ensures continuous current flow to the load. Capacitor. Output and input capacitors. Capacitors are used both at the input and output of the regulator. At the output, capacitors help to filter out noise and stabilize the output voltage. At the input, capacitors assist in filtering high-frequency noise from the power source and provide transient response. Feedback circuitry. Error amplifier and voltage reference. The feedback circuitry monitors the output voltage and compares it to a reference voltage. Any difference between the actual output voltage and the desired voltage is amplified and used to adjust the duty cycle of the switching element, maintaining the output voltage at the desired level. Control IC. Integrated circuit. In many modern switching regulators, the control circuitry, error amplifier, and other necessary functions are integrated into a single IC, integrated circuit. This IC may also include features such as overcurrent protection, thermal shutdown, and soft start functionality. External passive components. Depending on the specific design and topology of the switching regulator, additional passive components such as resistors, capacitors, and inductors may be required for compensation, filtering, and other purposes. These components work together within the switching regulator circuit to efficiently regulate voltage, providing a stable output voltage despite variations in input voltage and load conditions. Proper selection and design of these components are critical for achieving desired performance characteristics such as efficiency, transient response, and noise immunity. A buck regulator, also known as a step-down regulator, is a type of switching voltage regulator that converts a higher input voltage to a lower output voltage. Here's how a basic buck regulator operates. Topology. The buck regulator circuit typically consists of a switch, usually a transistor, an inductor, a diode, a capacitor, and control circuitry. Operation. On state. During the on state, the switch, transistor, is closed, allowing current to flow from the input source through the inductor and the switch to ground. As current flows through the inductor, energy is stored in its magnetic field. OFF state. In the off state, the switch is opened, interrupting the flow of current. The energy stored in the inductor's magnetic field is released, causing the inductor voltage to reverse polarity. The diode, also known as the freewheeling diode, provides a path for the inductor current to continue flowing, ensuring a continuous output voltage. Output voltage regulation. The output voltage is regulated by controlling the duty cycle of the switch. The duty cycle is the ratio of the on time to the total period, on time plus off time, of the switch. By adjusting the duty cycle, the average output voltage can be controlled. Higher duty cycles result in higher average output voltage, while lower duty cycles result in lower output voltage. Voltage conversion. Since the output voltage is lower than the input voltage, the average output voltage is controlled by adjusting the duty cycle. The inductor stores energy during the on state and releases it during the OFF state, effectively transferring energy from the input to the output while reducing the voltage. Efficiency. Buck regulators are known for their high efficiency because they minimize power dissipation. Unlike linear regulators, which dissipate excess energy as heat, buck regulators transfer energy to the output more efficiently by switching the transistor on and off rapidly. Applications. Buck regulators are commonly used in various electronic devices where a lower voltage is required, such as powering microcontrollers, digital circuits, sensors, and low-voltage devices. They are widely used in battery-powered applications to efficiently regulate the voltage from a battery to match the requirements of the load. Advantages. High efficiency. Buck regulators can achieve efficiencies greater than 90%. Compact size. They can be implemented with fewer components compared to linear regulators, making them suitable for space-constrained applications. Wide input voltage range. Buck regulators can operate over a wide range of input voltages, making them versatile for different power supply applications. Disadvantages. Voltage limitation. Buck regulators can only step down the input voltage. They cannot produce an output voltage higher than the input voltage. Output ripple. Depending on the design and load conditions, buck regulators may exhibit output voltage ripple, which may require additional filtering if critical for the application. Overall, buck regulators are widely used in various electronic devices and systems where efficient voltage step-down conversion is required. They offer high efficiency, compact size, and versatility, making them essential components in modern power supply designs. A boost regulator, also known as a step-up regulator, is a type of switching voltage regulator that converts a lower input voltage to a higher output voltage. Here's how a basic boost regulator operates. Topology. The boost regulator circuit typically consists of a switch, usually a transistor, an inductor, a diode, a capacitor, and control circuitry. Operation. On state. During the on state, the switch, transistor, is closed, allowing current to flow from the input source through the inductor and the switch. As current flows through the inductor, energy is stored in its magnetic field. OFF state. In the off state, the switch is opened, interrupting the flow of current. The energy stored in the inductor's magnetic field causes the inductor voltage to reverse polarity, generating a voltage across the inductor that is higher than the input voltage. This higher voltage is transferred to the output through the diode. Output voltage regulation. The output voltage is regulated by controlling the duty cycle of the switch. By adjusting the duty cycle, the average output voltage can be controlled. Higher duty cycles result in higher average output voltage. Voltage conversion. Since the output voltage is higher than the input voltage, the boost regulator achieves voltage step-up by storing energy in the inductor during the on state and releasing it to the output during the OFF state, effectively increasing the voltage. Efficiency. Boost regulators can achieve high efficiency, particularly at higher output voltages. However, efficiency may decrease as the input-to-output voltage difference increases. Applications. Boost regulators are commonly used in applications where a higher voltage is required than what the input source provides, such as powering LED drivers, LCD backlighting, and other devices requiring higher voltages than available from a battery or power source. They are also used in renewable energy systems, such as solar panel installations, where they step up the voltage from the solar panels to match the requirements of the load or the battery charging system. Advantages. Voltage step-up capability. Boost regulators can increase the voltage from a lower input voltage to a higher output voltage. Compact size. They can be implemented with relatively few components compared to linear regulators. High efficiency. Boost regulators can achieve high efficiencies, particularly at higher output voltages. Disadvantages. Limited input current capability. Boost regulators may have limitations on the maximum input current they can handle, depending on the design and components used. Output ripple. Depending on the design and load conditions, boost regulators may exhibit output voltage ripple, which may require additional filtering if critical for the application. Boost regulators are essential components in various electronic devices and systems where efficient voltage step-up conversion is required. They offer high efficiency, compact size, and versatility, making them suitable for a wide range of applications. A buck boost regulator is a type of switching voltage regulator that can both step up, boost, and step down, buck, the input voltage to maintain a stable output voltage. This versatility makes buck boost regulators suitable for applications where the input voltage can vary above and below the desired output voltage. Here's how a basic buck boost regulator operates. Topology. The buck boost regulator circuit combines the configurations of both buck and boost regulators. It typically consists of a switch, transistor, an inductor, a diode, a capacitor, and control circuitry. Operation. Buck mode. Step down when the input voltage is higher than the desired output voltage. The buck boost regulator operates in buck mode. During this mode, the switch, transistor, is turned on and off to control the flow of current through the inductor. Energy is stored in the inductor during the on state and released to the output during the OFF state, effectively reducing the output voltage. Boost mode. Step up conversely, when the input voltage is lower than the desired output voltage. The buck boost regulator operates in boost mode. During this mode, energy is stored in the inductor during the on state and released to the output during the OFF state, effectively increasing the output voltage. Output voltage regulation. The output voltage is regulated by controlling the duty cycle of the switch. By adjusting the duty cycle, the average output voltage can be controlled. The buck boost regulator seamlessly transitions between buck and boost modes to maintain a stable output voltage regardless of variations in the input voltage. Efficiency. Buck boost regulators can achieve high efficiency across a wide range of input and output voltages. However, efficiency may vary depending on factors such as the input-to-output voltage difference, load conditions, and circuit design. Applications. Buck boost regulators are commonly used in battery-powered devices and systems where the input voltage can fluctuate above and below the desired output voltage, such as portable electronics, automotive electronics, and renewable energy systems. They are also used in applications requiring bidirectional power flow, such as energy storage systems, battery chargers, and power supplies for telecommunications equipment. Advantages. Voltage step-up and step-down capability. Buck boost regulators can both boost and buck the input voltage to maintain a stable output voltage. Wide input voltage range. They can operate over a wide range of input voltages, making them suitable for applications with fluctuating input voltages. Compact size. Buck boost regulators can be implemented with relatively few components compared to using separate boost and buck regulators. Disadvantages. Complexity. Buck boost regulators are more complex than buck or boost regulators due to the need to seamlessly transition between buck and boost modes. This complexity may require more careful design and testing. Efficiency considerations. Efficiency may vary depending on the input-to-output voltage difference and load conditions. Designers must carefully consider these factors to optimize efficiency for their specific application. Overall, buck boost regulators offer versatility, efficiency, and compactness, making them essential components in various electronic devices and systems where stable voltage regulation is required across a wide range of input voltages. A flyback regulator, also known as a flyback converter, is a type of switching voltage regulator commonly used in isolated power supply applications. It provides galvanic isolation between the input and output circuits, making it suitable for applications requiring safety isolation or where there's a need to eliminate ground loops. Here's how a basic flyback regulator operates. Topology. The flyback regulator is based on a transformer and typically consists of a switch, transistor, a transformer, a diode, a capacitor, and control circuitry. Operation. On state. During the on state, the switch, transistor, is closed, allowing current to flow from the input source through the primary winding of the transformer. Energy is stored in the transformer's magnetic field. OFF state. In the off state, the switch is opened, causing the magnetic field in the transformer to collapse. This induces a voltage across the secondary winding of the transformer, which is rectified by a diode to produce the output voltage. Output voltage regulation. The output voltage is regulated by controlling the duty cycle of the switch. By adjusting the duty cycle, the energy transferred to the secondary winding, and hence the output voltage, can be controlled. Isolation. The primary and secondary windings of the transformer provide galvanic isolation between the input and output circuits. This isolation ensures safety and eliminates ground loops that may cause interference or safety hazards in the system. Efficiency. Flyback regulators can achieve high efficiency, particularly at low power levels. However, efficiency may decrease at higher power levels due to factors such as transformer losses and switching losses. Applications. Flyback regulators are commonly used in applications requiring isolated power supplies, such as battery chargers, LED drivers, telecommunications equipment, and industrial control systems. They are also used in offline power supplies, where they can provide isolation between the mains input and the output circuits. Advantages. Galvanic isolation. Flyback regulators provide isolation between the input and output circuits, enhancing safety and eliminating ground loops. Versatility. They can be used in a wide range of applications requiring isolated power supplies. Compact size. Flyback regulators can be implemented with relatively few components, making them suitable for space-constrained applications. Disadvantages. Voltage and current stresses. The transformer in a flyback regulator must withstand high voltages and currents, which may require careful design and selection of components. EMI considerations. Flyback regulators may generate electromagnetic interference, EMI, due to the switching action of the transistor and transformer. Proper filtering and shielding may be necessary to mitigate EMI issues. Overall, flyback regulators offer efficient and isolated power supply solutions for various applications, particularly those requiring safety isolation or where ground loops need to be eliminated. Proper design and implementation are essential to ensure reliable and stable operation in the intended application. A forward regulator, also known as a forward converter, is a type of switching voltage regulator commonly used in power supply applications, particularly in low to medium power ranges. It operates by transferring energy from the input to the output through a transformer, providing galvanic isolation between the input and output circuits. Here's how a basic forward regulator operates. Topology. The forward regulator typically consists of a switch, transistor, a transformer, a diode, a capacitor, and control circuitry. Operation. On state. During the on state, the switch, transistor, is closed, allowing current to flow from the input source through the primary winding of the transformer. Energy is stored in the transformer's magnetic field. OFF state. In the off state, the switch is opened, causing the magnetic field in the transformer to collapse. This induces a voltage across the secondary winding of the transformer, which is rectified by a diode to produce the output voltage. Output voltage regulation. Similar to other switching regulators, the output voltage is regulated by controlling the duty cycle of the switch. By adjusting the duty cycle, the energy transferred to the secondary winding, and hence the output voltage, can be controlled. Isolation. Like the flyback regulator, the primary and secondary windings of the transformer in a forward regulator provide galvanic isolation between the input and output circuits. Efficiency. Forward regulators can achieve high efficiency, particularly at low to medium power levels. However, efficiency may decrease at higher power levels due to factors such as transformer losses and switching losses. Applications. Forward regulators are commonly used in applications requiring isolated power supplies, such as battery chargers, LED drivers, telecommunications equipment, and industrial control systems. They are particularly suited for applications with higher power requirements compared to flyback regulators. Advantages. Galvanic isolation. Forward regulators provide isolation between the input and output circuits, enhancing safety and eliminating ground loops. Higher power capability. Forward regulators are suitable for applications with higher power requirements compared to flyback regulators. Efficiency. They can achieve high efficiency, particularly at low to medium power levels. Disadvantages. Complexity. Forward regulators may be more complex to design and implement compared to simpler switching regulators such as buck or boost converters. Voltage and current stresses. The transformer in a forward regulator must withstand high voltages and currents, which may require careful design and selection of components. EMI considerations. Similar to other switching regulators, forward regulators may generate electromagnetic interference, EMI, due to the switching action of the transistor and transformer. Proper filtering and shielding may be necessary to mitigate EMI issues. Overall, forward regulators offer efficient and isolated power supply solutions for various applications, particularly those with higher power requirements. Careful design and implementation are essential to ensure reliable and stable operation in the intended application. Forward regulators offer several advantages in power supply applications. Efficiency. Forward regulators can achieve high efficiency, particularly at low to medium power levels. This efficiency is due to the switching nature of the regulator, which minimizes power dissipation compared to linear regulators. High efficiency leads to less wasted energy, reducing heat generation and improving overall system reliability. Galvanic isolation. Like other isolated switching regulators, forward regulators provide galvanic isolation between the input and output circuits. This isolation enhances safety by preventing direct electrical connections between different parts of the system. It also helps to eliminate ground loops, reducing the risk of noise and interference. Higher power capability. Forward regulators are suitable for applications with higher power requirements compared to some other types of switching regulators, such as flyback converters. This makes them well suited for applications where higher output power levels are necessary, such as in industrial equipment, telecommunications infrastructure, and power distribution systems. Low output ripple. Forward regulators typically exhibit lower output voltage ripple compared to other types of switching regulators, such as buck-boost converters. This is beneficial in applications where a stable output voltage is required, such as in sensitive electronic equipment or systems requiring high-quality power. Wide input voltage range. Forward regulators can often operate over a wide range of input voltages, making them suitable for use in diverse applications where input voltage levels may vary. This versatility allows them to be used in both AC and DC input power sources, including mains power and battery systems. Compact size. Forward regulators can be designed to be relatively compact, making them suitable for space-constrained applications where minimizing size and weight is important. This compactness is achieved through efficient switching operation and integration of components, enabling the design of smaller and lighter power supplies. Adaptability. Forward regulators can be configured to meet specific application requirements by adjusting parameters such as output voltage, current capability, and efficiency. This adaptability makes them versatile and suitable for a wide range of applications, from consumer electronics to industrial machinery. Overall, the advantages of forward regulators make them a preferred choice for many power supply applications where high efficiency, galvanic isolation, and reliable performance are essential requirements. While forward regulators offer various advantages, they also have some limitations and disadvantages. Complexity. Forward regulators can be more complex to design and implement compared to simpler switching regulators like buck or boost converters. The transformer design, control circuitry, and feedback mechanisms may require careful consideration and optimization, adding to the complexity of the system. Voltage and current stresses. The transformer in a forward regulator must withstand high voltages and currents, which can lead to increased stress on the components. This may require the use of specialized components with higher voltage and current ratings, increasing the cost and complexity of the system. EMI considerations. Similar to other switching regulators, forward regulators can generate electromagnetic interference, EMI, due to the switching action of the transistor and transformer. Proper filtering and shielding may be necessary to mitigate EMI issues and ensure compliance with electromagnetic compatibility, EMC, standards. Limited voltage regulation range. Forward regulators may have a limited voltage regulation range compared to other types of switching regulators. This limitation can restrict their suitability for applications with wide variations in input or output voltage requirements. Size and weight. While forward regulators can be relatively compact compared to linear regulators, they may still be larger and heavier than some other switching regulators, especially at higher power levels. This can be a disadvantage in applications where space and weight constraints are critical considerations. Efficiency trade-offs. Achieving high efficiency in forward regulators may require careful design and optimization of the circuitry, especially at low loads or high input-output voltage differentials. Efficiency may decrease under certain operating conditions, affecting overall system performance and energy efficiency. Cost. The complexity of forward regulators, as well as the need for specialized components such as transformers and control circuitry, can contribute to higher overall system costs compared to simpler switching regulators. This can be a disadvantage in cost-sensitive applications or when designing products for mass production. Heat dissipation. While forward regulators are generally more efficient than linear regulators, they still produce some heat due to switching losses and other inefficiencies. Proper thermal management may be required to ensure reliable operation and prevent overheating of components, especially in high-power applications. Overall, while forward regulators offer several advantages, designers must carefully consider these disadvantages and trade-offs when selecting the appropriate regulator for a specific application. Each application's requirements and constraints will dictate the most suitable choice. Forward regulators find applications in various industries and electronic systems where isolated and efficient power conversion is required. Some common applications include telecommunications equipment. Forward regulators are widely used in telecommunications infrastructure, including base stations, network switches, routers, and telecom power supplies. They provide isolated power supplies for sensitive electronic components and help ensure reliable communication networks. Industrial control systems. Industrial equipment and automation systems often require isolated power supplies to protect sensitive electronics from electrical noise and ensure safety. Forward regulators are used in PLCs, programmable logic controllers, motor drives, robotic systems, and instrumentation equipment in industrial settings. Power distribution systems. Forward regulators are employed in power distribution systems for voltage regulation and isolation. They are used in DC-DC converters for power distribution in data centers, server farms, and renewable energy systems such as solar and wind power plants. Medical devices. In medical equipment and devices, such as patient monitors, imaging systems, and medical instruments, forward regulators provide isolated and stable power supplies to ensure patient safety and reliable operation in sensitive medical environments. Consumer electronics. Forward regulators are used in various consumer electronics applications, including LED drivers, audio amplifiers, and power adapters. They provide isolated power conversion for components such as displays, audio circuits, and microcontrollers in devices like TVs, monitors, and audio equipment. Automotive electronics. In automotive applications, forward regulators are used in power management systems, battery charging systems, LED lighting, and electric vehicle (EV) charging stations. They provide isolated power supplies for critical components and ensure efficient power conversion in automotive systems. Aerospace and defense. Forward regulators are utilized in aerospace and defense applications, including avionics systems, radar systems, communication equipment, and missile guidance systems. They provide isolated and reliable power conversion in harsh environmental conditions and ensure the performance and safety of critical systems. Renewable energy systems. In renewable energy applications such as solar inverters and wind turbine systems, forward regulators are used for DC-DC conversion, voltage regulation, and isolation. They enable efficient power conversion and integration of renewable energy sources into the electrical grid. Overall, forward regulators play a vital role in various industries and electronic systems where isolated and efficient power conversion is essential. Their versatility, reliability, and ability to provide galvanic isolation make them suitable for a wide range of applications across different sectors. Overall, switching voltage regulators are essential components in modern electronics, offering high efficiency and flexibility in voltage regulation across a wide range of applications. However, their design and implementation require careful consideration of factors like efficiency, cost, and electromagnetic compatibility, EMC.